Hello there. Thank you for clicking on this video. I just had a cat plunk itself down in my lap, so we're going to see how this goes with writing. Welcome to this practice set on exponential equations. This practice set focuses on like bases. Please like and subscribe if you find the practice set helpful for you. Ask me a question or give feedback in the comments, and check out the many other videos and playlists on the channel. I'll be sure to link some at the end of this video. So as always, pause the video to work these problems on your own, then come back to check your work. Okay, let's take a peek at these. So these are actually scaffolded up. So I did try to, when I wrote these problems, go in order of increasing difficulty. So if you notice that, the cat just decided to leave. So I guess she's not a fan of exponential equations. I don't know what's wrong with her. Anyway, if you felt that they were getting a little bit more difficult or challenging as you went through, that was intentional. So the first one is pretty much I don't want to say like regurgitation, but an assessment of understanding the basic principle. Like, are you going to do something with this other than what you should do? So 5 to the 2x equals 5 to the 6th power. So once we have the like bases, we are allowed to set the two exponents equal. And so 2x is equal to 6. Divide both sides by 2, and x is equal to 3. Now, what I mentioned this in the instructional video, so if you just hopped over here from there, this will be pretty close together, but if you had a break or you're just doing the practice set and not the lesson, this would be incorrect, okay? It is incorrect to write that there is division happening. Okay, I'm going to circle that like I did in the lesson, and I'm going to draw like the line through it. We'll just do two, like no, 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 and no. There is no division happening here, and that can be a classic example of where you could land with the right answer, but evidence a misunderstanding about the actual arithmetic and processes involved in this. Division is used to undo multiplication, and an exponent, while you could argue that an exponent was repeated multiplication, I guess the key there is it's repeated, and we do not know how many times it's been repeated. So when we have 5 to the 2x, okay, the x is the variable. You could, I guess, divide the, you say, well, I know that the 5 to the 6th is multiplied in 5 times, but like, let's just chase this rabbit for a moment. If you're saying 5 to the 6th power and you're dividing it and you're saying that's equal to 6, that is flat out incorrect. Okay, and a math teacher who is looking at your work should rightfully take off for that. 5 to the 6th power divided by 5, that's 5 times 5 times 5 times 5 times 5. And you're dividing it by 5. There, you are left with 5 to the 5th power, which is most definitely not a 6. Okay, and so that is one of those things that we need to get out of in case you find yourself falling into it. But I got the right answer, which means if you were doing this on a multiple choice test or something, you would be fine. But what that work is showing is a bona fide misconception about the actual processes that we're going through here. So if that happened in my class, I would take off points for that because it is not correct to indicate that there is division happening there. So make sure you fix that if you're realizing that you did do that on your scratch work, that you make a note to yourself. Okay, second one is similar to the first one in that we already have the like bases. It's a little bit more challenging in that we have now messed with the exponents. So now we have x's on both sides, but it doesn't change that key rounding idea. If you have the same base, then you may set the exponents equal. So x minus 6 is equal to 4x plus 3. I'm going to go ahead and subtract x from both sides to get negative 6 is equal to 3x plus 3. And then we'll subtract the 3. So negative 9 is equal to 3x. Divide both sides by 3, and we get x is equal to negative 3. So what we're doing here is we're using the like bases to essentially be able to set the exponents equal and not have to deal with the exponentialness of it anymore. But we are definitely not dividing. If you wanted to make up a word like we are de-exponentializing it, totally fine. We are de-exponentializing it, but we are not dividing. That's definitely not what we're doing. Okay, so going into this next one, on this next one, I do try to vary these a little bit. It can be very easy to get into like some habits if you're the teacher and you're writing these you kind of start to make all the problems look the same way without even realizing it. So I try to put the sides that we're messing with on different sides of the equal sign there. Now, if the bases don't match, then the challenge becomes, how can I get them to match? Okay, so can I rewrite this? This would fall under a larger umbrella of what's called equivalent forms. So taking an expression and writing it in some different way, but that is equivalent. And general strategy here, and in the lesson, I call this like the scratch/calculator work. Okay, I don't require my students to show this to me because they might not even need to do it because the numbers do stay fairly small. But we're going to take this smaller number and keep raising it to powers to see if we can get the larger number. So 5 to the first power is 5, 5 squared is 25, 5 to the third is 125, and we've got it. What's about to happen over here on the left is I am going to take out the 125. So I'm pulling out the 125 and I'm replacing the 125 with 5 to the third. And I can do that because that is equivalent. Now, in the video, I use the illustration of the Super Cool Exponent Club. And the Super Cool Exponent Club is not a friendly club. This is the x plus 2. It is the original exponent, and the 125 is being raised to that exponent. Therefore, 5 to the third power must also be raised to that exponent. And so the way I illustrated is they are not a friendly club, and they put up their super cool exponent walls and they try to shut out the newcomer to the exponent. So think of it as an exclusive club, and when this 3 here wants to bust into being the exponent, like let me in to be the exponent, they say nope, 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 nope. Now, the point of the analogy or story is to preserve the order of operations there by remembering that we need to group that together. Once you have that, now you've got both sides as a power of the same base. And so we can set the exponents equal. And if I were doing this on my own, I would jump straight here. Okay, in other words, I would do that distribution 3x plus 6 on my way down, and I would skip this step. I would not write this separate step of the two exponents equal. I would distribute as I came down. And now we've accomplished what we needed to. We got rid of the exponentialness of this, and we can just solve that. So I'm going to subtract 3x from both sides, and I will be left with 6. 4x minus 3x is x. And so x is equal to 6. Next one is 81 to the 3x minus 1 equals 27 to the x plus 5. Well, I don't think I even want to mess with powers of 27, okay? Because I can tell you right now, 27 squared is going to be way too big. We are going to overshoot the 81 by a bunch. But you could try this if you want, okay? We have our scratch/calculator work. And we have 27 to the first power is 27. 27 squared is huge. Okay, done. You throw it into a calculator if you want. It's big. When this happens, what we do is we look at the two numbers and we think, is there a smaller number that we could use that would work to rewrite both of them? So the good news here is that there's a very limited number of numbers that will work because exponentials do get huge. So we're dealing often with 2s, 3s, 4s, and 5s. Anything bigger than that starts to get a little bit unwieldy. So if you've done any kind of work with your exponents, you probably have an intuition that the number that we're going to go for here is 3. So 3 to the first power is 3, 3 squared is 9, 3 cubed is 27, so that gets me the 27, and 3 to the fourth power is the 81. So on this equation, I am going to take out the 81. The 81 is physically coming out of the problem, and we're going to replace the 81 with 3 to the fourth because that is the same thing. We have an exponent there. Remember, the exponents in these equations are not friendly. And so the 3x minus 1 is not welcoming the new exponent of 4, saying nope, 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 nope. Now, going on the other side over here, we are taking out the 27 and we're replacing the 27 with 3 to the third. And once again, the exponents in these problems are not friendly. So we have the super cool exponent club putting up these walls and saying, nope, we are not admitting new members to our club. Once we have the same base, so we have each side written to a power of 3, then we are able to set the exponents equal. And you are welcome to distribute as you're writing it down. So you might say 12x minus 4 equals 3x plus 15. Or if you need to, you can copy the two exponents down like so, and then do the distribution. Okay, that is up to you. All right, so we have a linear equation here. So let's go ahead and solve that for x. We'll be subtracting 3x from both sides. So 9x minus 4 equals 15. Add 4 to both sides. So 9x equals 19. And divide both sides by 9 to get x is equal to 19 over 9. And I'm not messing with that. Okay. That cannot be simplified because 19 is a prime number, and I also don't want to simplify it. Now notice most of this is the linear equation, and what I've told my students is if you can get here, then your exponential skills are good. Then you understand how to deal with the exponential part. If you are getting here and then messing up in this part down here, that is linear equations. So if you want to fix the problem, you need to go back and study some linear equations. And obviously I have a ton of stuff on the channel here that can walk you through the basics of solving linear equations, all the way from one-step equations up through all your multi-step equations. And you can watch some lessons and dive deep into that so that you can bring your linear equation skills on board with your exponential equation skills. Okay, so these two are meant to stretch the limits and review some stuff. So this one here, you can probably guess that the number we want to get is a 6. The problem is this 6 is stuck underneath a square root. And if you have followed along with some of my other lessons, then you know that this goes back to what are called rational exponents. And what I always tell my students is if there is one thing you take out of a lesson on rational exponents, it is this: a square root is an exponent of 1/2. So the square root of 6 is 6 to the 1/2. For a detailed explanation as to why that is the case and what you would do if you saw some root other than a square root, like let's say you saw a cube root or a fourth root, okay, probably you won't, but maybe you would, then what you would do, please see my video lesson on rational exponents. If I can remember to, I'll go ahead and link that up here so that you can check that out if that is something that you need to see. Now I've got my like bases, so I have my 6 on both sides. So 1/2 is equal to x over 4. And I just went over this the other day with my classes because we see fractions and the wheels fall off of everything. But we need to ask ourselves a leading question. I actually told my classes, I'm going to ask you a leading question that is going to steer how you're thinking in the right direction. And what you need to do is learn how to ask yourself that question. And the question is, what is the 4 doing to the x? And then sometimes I get way too much variety in the answers because students will actually jump much, much further ahead with that, and they will say multiplying. And I'm like, no, that's the answer to the next question. What the 4 is doing is it is dividing. And once you can conclude that the 4 is dividing, that directs how you're going to proceed with solving it. So if the 4 is dividing, the way we undo dividing is by multiplying. And that's why I will often tell students, like, nope, that was the next question. So if I divide by 4 and multiply by 4, now I'm left with just x, and 4 times 1/2 is 4 halves, or 2. Ta-da. Next one. I was actually just kind of going crazy with these when I was writing them earlier, and kind of just decided I was going to make them as crazy as possible. So this one also does this requires some review from potentially a previous unit where we have studied exponents in general. But hopefully what you can see from this is that the common base that we're going to be looking for is a 4. So you see the 4 on the right, and then you see the 16. And hopefully we do remember this, that 16 is equal to 4 squared. So the first thing you might do is rewrite the 16 as a 4 squared. And now from here, you need to remember some laws of exponents. So we don't want everything that we have ever learned to just go flying out the window. And it's this. If you have like a number with a negative exponent on it, that's 1 over that, like a positive exponent. So basically a negative exponent means a reciprocal. Now, oftentimes, what we're doing is we're dealing with a negative exponent and we're trying to get rid of the negative exponent. But in this case, we are actually starting with this as a fraction, and we're saying, but I don't want to write that as a fraction. And so the way we get rid of the fraction is by using the negative exponent. So 1 over 4 squared is actually 4 to the negative 2. And now we have our like bases, therefore we can set our exponents equal. So negative 2 is equal to 2x. Divide both sides by 2, and negative 1 is equal to x. So a couple of review things with exponents. I mentioned at the end of the lesson video, like, hey, the practice set is going to have some twists and turns in it. And this is what I meant by some twists and turns. So we need to like dig up some old knowledge and put that into practice here. Okay, I think I've got more of this. I don't even remember what I did with this. So let's see. So we have 1 over 2 to the x is equal to 4 to the x. This is fun. So looking at what we just did, 1 over 2 to the x is 2 to the negative x. Okay, so right off the bat, like engaging what we just went over. Now we've got unlike bases still. So we still have the issue of I have a 2 on one side and a 4 on the other side. And so we would take that 2 and just kind of play with it. And this is why I don't require my students to show this, because I think most of my students do know this. And so we're going to take out the 4 and replace that with a 2 squared. Now you can put up the cool exponent walls on that. It won't make any difference one way or the other because 2 times x is just 2x. You don't have distribution. Okay, so you don't really need it there because of the absence of distribution. But if you're in the habit of putting them there, like there's no problem with that. And once again, we have our like bases, therefore our exponents would be equal. So negative x is equal to 2x. And you can do this a couple different ways. I am going to add x to both sides, I guess. Negative x plus x is 0 is equal to 3x. And from here, you could probably reason it out, like 3 times what would give me 0? Well, it would have to be 0, or you can do the algebra out and divide both sides by 0. 0 divided by 3 is 0. And so x in this case would have to be equal to 0. Now, if you're like, oh, wait a minute, does that even check? Why, yes, it does. Okay, so 1 over 2 to the 0, does that equal 4 to the 0? Yes, because anything raised to the 0 power except 0 is 1. So that's 1 over 1 is equal to 1. And you can see that it does check. Next one is this. What are 2 ways that you could solve the equation below using like bases? So there's actually, no, I guess there's just the 2 ways to do this. I think I'm thinking of if I had a 4 there. Yeah, if I had a 4 there, we would have a little bit, instead of an 8, we would have more flexibility. But one way you could do this one is by changing the 64 over to 8 squared. So is like going straight to this and saying, okay, 8 squared is 64, and so that's 8 squared. And if you want to put up the exponent walls there, because you don't want to accidentally end up with a exponent of 23, that would be really bad. And okay, so you can convert the 64 over to a base of 8, and then we get our exponents are equal. So x is equal to 2 times 3 or 6. So yay. So now you get the challenge of, okay, well, what else could I do? And so this one might require a little bit of gymnastics, but both 8 and 64 can be written as powers of 2. And so if we kind of go through this, this is our scratch work down here. 2 to the first power is 2, 2 squared is 4, 2 to the third is 8, so that gives me the 8. 2 to the fourth is 16, 2 to the fifth is 32, and 2 to the sixth is 64. So the other way you could do this is replace the 8 with 2 to the third and replace the 64 with 2 to the sixth. And so now we would have 3x is equal to 6 times 3. And right here, you can divide both sides by 3, like just cancel out the common factors. Or if you want to, you can multiply them through and then divide by 3. And I had a student in my class, there was one on a homework assignment that I gave to my class that was like this, and a student was like, well, I did it differently. And what they had done was they had like shrunk it down to a smaller base instead of using a larger one. And this is just a good illustration of there being more than one way to do it, that are even using the same strategy. There's more than one way to do it. And if you're observant, you kind of want to try to find the easier of the 2 ways, but at the end of the day, it honestly doesn't matter. All right, last 2 problems. Can this equation be solved using this strategy? So this is a yes, no question. Can you solve 3 to the x equals 10 by using this strategy? So you might tinker around with this, or you might intuitively know no. No, and the reasoning there is because 10 cannot be a power of 3, at least not a power that we know. Now, when I introduce this to my students, we do talk about it, and we also go through a little bit of like guess and check stuff going on to see like how close we can get. So that brings us to question 10, which is, well, what do I know about the solution to number 9? Because we're not in the dark. And when I do this in my classes, it's really fun to watch how students start thinking about it. So I have had students just start with saying, well, x isn't 1. Okay, fair enough. Like, and so we'll start with that. Like, x does not equal 1. And then, somebody might say, well, x doesn't equal 2. And I'll just follow with that. And eventually, though, a student might get more specific than that, and they'll say, well, I know more than that. It's just not equal to 2. I know that it is greater than 2. And so they might start doing this sort of thing. 3 squared is equal to 9, which means that 2 is coming up a little bit short off of what we're looking for there. Therefore, whatever the value of x is, it must be greater than 2. And once a student says that, somebody else will come up with this. Well, x has to be less than 3. And I'll often write it like this on the board as students are kind of coming up with that idea that we're looking for a number in between the 9 and the 27. Therefore, the value of x must be in between 2 and 3. So if you've got a number line, we have now narrowed down the value of x to somewhere in here. And then what I will often do then as a bit of a leading question, and sometimes students will get here as well without me leading with a question, is I'll ask, well, which is it closer to? Is x closer to 2 or closer to 3? And I don't know if I've ever had a class get this wrong. They will say it is closer to 2. Now, how much closer to 2, we don't actually know because this is not linear, this is exponential. But we can be pretty confident that because 10 is so much closer to 9 than it is to 27, that x should be closer to 2. So we're thinking somewhere here. So x is somewhere in there. And the point of this is to empower students to recognize that just because you do not know how to solve an equation does not mean that you are helpless at knowing some things about it. I'll say this, if this were a multiple choice question and these were your answer choices, okay, what one would you pick? And we now know that we are going to pick B because we know it is between 2 and 3, and it is closer to the 2 than it is to the 3. So therefore, 2.1 would be the one we'd pick, which means that you can get this question right even if nobody teaches you how to solve it. Even without a calculator, you could get a multiple choice question right. The other reason I like to bring this question up is because it introduces the need for another strategy. So we cannot solve all exponential equations by writing them as powers of the same base. It brings us to the point of, okay, well, I need another way to be able to do this. And that way is introduced in the next couple lessons on logarithms. So please don't forget to like and subscribe if you found this video helpful. Drop a comment below and let me know what you think. And please check out the many other videos and playlists on the channel. We've got multiple choice playlists. We've got Desmos playlists. We've got algebra tiles. We've got all of algebra 1. We have stuff on lines and quadratics and all the things. So please check out some other videos, and I hope to see you in a future video.